Hi students, welcome to Govidya. As part of previous year question solutions, today also we are going to solve some more questions related to the electrical transformers. Okay, in continuation to the previous session, we are solving the questions. Okay, let's look into the given question. The given question is about in a transformer, the core is laminated to reduce. Okay, what is the concept they're asking? The concept is about core design. Okay, core design of transformer. Okay, let's see the options. Based on that, we will select the suitable option for the given question. The first option is given as copper losses in the core. Okay, copper losses in the core. In general, the copper losses we are considering in a transformer. Significant amount of copper losses we are considering in a transformer is in windings. Okay, the copper losses are at windings at full load condition, but not in the core. This is not correct. Hysteresis losses. We already discussed hysteresis loss is mainly depends on the excitation. That means hysteresis loop, retentivity and coercivity properties. Okay, this may not affect the core design. Next is hysteresis and eddy current losses. Okay, we'll see first eddy current losses. What is eddy current losses? In a transformer, if you see, the core is, we are selecting a silicon steel here. We are using. Okay, and if we are exciting a transformer with an voltage V, flux will start flow in the transformer. Okay, the waveform of flux will be in sinusoidal. Okay, the waveform of flux is sinusoidal. The flux is varying with the time. And core is stationary. As per Faraday's law of electromagnetic induction, if there is a space variation or time variation between the conductor and flux, then an EMF will get induced. Here if you see, our core is a silicon steel. It is a one metal, or you can consider it as a conductor. Okay, it is there is a time variation. Our core is stationary, but flux is varying with respect to time. So there is a time variation between the core and flux. Then an EMF will get induced. Okay, EMF will get induced. So whenever an EMF will get induced in a transformer, it will develop some circulating currents. Inside the core. These currents are unwanted currents. What will happen? These currents lead to the I square R losses. That means because of these eddy currents, these circulating currents are called eddy currents. These eddy currents will leads to the I square R losses. These losses are called eddy current losses. Okay, eddy current losses. So in order to reduce this eddy current losses, what you are doing, this is a solid core. If you are using a solid core, then what will happen? More eddy currents will be there and more losses will be there. In order to reduce those eddy current losses, we are making the core into thin sheets. Like this. Okay, small slices we are cutting and laminated. Okay, each sheet is going to be painted with enamel paint, so that each thin plate is going to have some insulation. By that we are reducing the conductivity. Thereby we are reducing the I square R losses. So our suitable option is eddy current losses only, not the hysteresis losses. In a transformer, the core is laminated to reduce eddy current losses only. Our option is D. Is it clear? Okay, let's move on to the next question. The next question is about in a short circuit test of single phase. Here some mistake happened. I think it will be 4000 kVA. It will be 4000 kVA, 200 by 400 volt, 50 Hz transformer gave following results. So what they are telling, what is the concept related here? Concept related is short circuit test of transformer. Short circuit test of transformer. We have to remember the synopsis immediately. Whenever you are getting a question related to short circuit, any concept, we have to remember the synopsis in your mind. We have to rewind the synopsis in your mind. What are the synopsis we have to remember? Short circuit test we are conducting at HV side and LV side rated current will flow. Thereby we are getting the rated copper losses. That is the first point. Second thing is what the second point? We can get the percentage R and percentage R from the short circuit test. Okay, we can calculate percentage R per unit R from short circuit test. Okay, and full load copper losses also you can find out. Okay, this is the main synopsis we need to remember. Let's note down the given data. What is the given data? The transformer kVA is 4000. Voltage is given as voltage ratio. You can take it as 200 by 400. Okay, the test is conducted at HV side. Okay, the required voltage to generate rated current in LV side is 15 volts. Okay, current taken by LV side is 10 amps and power consumption during the test is 80 watts. What they are asking? Percentage regulation we need to calculate. Okay, at unity power factor. Okay, what they are asking? Percentage regulation at rate unity power factor. Need to find out. Okay, we know the percentage regulation formula. Percentage regulation is equal to percentage R cos pi plus percentage X sin pi. Okay, percentage R cos pi plus percentage X sin pi. Since power factor is unity, cos sin pi is going to be 0. So percentage regulation is nothing but percentage R cos pi. Cos pi is 1. It is you can write it as percentage regulation for unity power factor is percentage R. So if you are able to find the percentage R from the given data, then you can calculate the percentage regulation. Is it clear? Okay. So how to calculate the percentage R from the given data? That is from short circuit test. We know that whatever the power is taken from the source during short circuit test is completely to meet the copper losses. Okay, to meet the copper losses. If you are taking the resistance in percentage R, this indicate the full load copper losses only. Percentage R is nothing but full load copper losses. This is also called per unit resistance. Per unit resistance. All are equal terms. Okay, all are equal terms only. So now we will calculate the full load whatever the power consumption is in the short circuit test is to meet the full load copper losses only. Okay, so how to calculate percentage R? They given WSC. WSC is short circuit energy consumption during power consumption during short circuit test. WSC divided by what is the kVA? kVA into 100. What is the kVA given? 4000. What is the WSC given? 80. So let's do the cancellation here, and here it will going to be 2. Okay, therefore percentage R equal to 2%. Percentage R equal to 2%. Okay, our option is A. Our option is A. Is it clear? Hope it is clear for all. Let's move on to the next question. Let's move on to the next question. Okay, the next question is given about the primary turns of 444 volt divided by 222 volts 50 Hz single phase transformer with a core cross sectional area of 100 centimeter square and maximum flux density of 1 Tesla. Okay, so by reading the given question, we came to know that the concept is about calculation of induced EMF. They are asking about the primary turns of. Okay, so the primary turns of, they are asking primary turns. Okay, they are asking concept of induced EMF. From that we have to calculate primary turns N1. Okay, so what is the let's note down the given data. Later we will write down the known formula for us. The given data is primary voltage E1 is equal to 444, E2 equal to 222, and cross section area AN is equal to 100 centimeter square. Okay, and flux density B is equal to 1 Tesla. Okay, 1 Tesla. Before solving any question, we need to look out the units. Okay, you need to look out the units. Here it is given as centimeter square. Okay, we need to calculate all units in same form. That means a meter square form we have to bring that. We need to calculate the area in meter square. How much it will come? 100 into 10 power minus 4 meter square. And for flux density units are Tesla or Weber per meter square. Both are same. Okay, so let's look into the formula. What is the known formula for us? By using the given terms, induced EMF E1 is equal to 4.44 into pi into F into T. Okay, frequency also given, frequency is equal to 50 Hz. Okay, but we don't know pi, but we can replace pi with flux density. Okay, flux density into net area. If you do this, you can get the pi. Okay, let's substitute the given data. 4.44. What is the pi? Even is 444. B is given as 1 Tesla. Frequency is 50. 1 Tesla. Wait. 1 Tesla into 10 power minus 4 into frequency is 50 Hz. T we need to find out. T can be 444 divided by 4.44 into 10 power minus 4 into 50. How much it will come? Can you please calculate and tell? it will come around 200 tons. So therefore T is equal to 200. Our option is B. Is it clear? Let's move on to the next question. Okay, the next question is about the condition for maximum regulation of single phase transformer with equivalent resistance R equivalent. Okay, and equivalent reactance and load power factor angle pi. Okay, first of what is the concept they are asking about? The concept is about voltage regulation. Concept is about voltage regulation. The approximate equation for voltage regulation is, we can write it as 1 by V into R cos pi, R equivalent cos pi plus X equivalent sin pi. Okay, the approximate equation. They are asking about maximum regulation. Okay, they are asking about maximum regulation. So we already seen a voltage regulation curve. Voltage regulation curve, if you see, it will be like this. Okay, the maximum will occur for lagging power factor, and it is varying with pi. Percentage regulation is varying with pi. So we need to differentiate the equation 1 and equate to 0 for getting maximum voltage regulation with respect to pi. If you do that differentiation of d by dt of 1 by V R equivalent cos pi plus X equivalent sin pi, how much it will come? Equal to 0. For getting maximum, we have to make the differentiation equal to 0. So from this, what you will get? R equivalent into cos pi differentiation will be minus sin pi. X equivalent into sin pi differentiation will be cos pi equal to 0. Therefore, X equivalent cos pi equal to R equivalent sin pi. You can write it as sin pi by cos pi equal to X equivalent by R equivalent. This can be written as, therefore, tan pi equal to X equivalent divided by R equivalent. This will be R equivalent. Okay, so our option will be D. Okay, so our option will be D. Tan pi equal to X equivalent by R equivalent. Is it clear? Let's move on to the next question. The next question is about the main application of delta by zigzag connected three-phase transformer is to supply. Okay, actually it is a special type of not special type, it is one type of three-phase transformer connection. Okay, delta, what we need to remember regarding this type of connection is, it is a delta to zigzag transformer. Zigzag. What is the main purpose of this is, in secondary winding you can get the neutral point. First thing, what and all points we will note down. You are getting neutral point in secondary. What is going to happen if you are having if you are having primary as delta and the secondary as a zigzag connection, then you can get a neutral point such that you can connect single phase loads. Can connect single phase loads to a single phase loads to the transformer. And this is first point. Coming to the second point, since these zigzag transformers will nullify the third harmonic currents. So why? Because if we are connecting a single phase loads, that may be a unbalanced loads also, but this may affect to the primary side. Delta is a primary side, their voltage may get disturbance because of the harmonics. So in order to avoid that condition, we are using a delta to zigzag transformer. This zigzag transformer is having a special application, such as it is going to nullify the third harmonic current. Thereby we can use this connection for unbalanced single phase loads also. So our option is B. So what we need to remember is, in delta zigzag transformer there is a availability of neutral in the secondary side, so you can connect single phase loads also. And one more advantage is, it is going to nullify the third harmonic currents. Thereby if the load is unbalanced, the third harmonics will get generated. This is going to nullify secondary side itself. It won't reflect on primary side. So our primary side voltage will be stable and balanced. Is it clear? So this delta zigzag transformer we are using only for, especially for unbalanced loads. Okay, let's move on to the next question. The next question is about two transformers having the same per unit impedance connected in parallel share the connected load. Okay, so by reading the question, the question is about parallel operation of transformer. What is the given data? Given data is per unit impedance, Z per unit 1 equal to Z per unit 2. They are taken two transformers, both per unit impedance are equal. Okay, when per unit impedances are equal, what is going to happen? We know that load sharing is inversely proportional to the Z. Okay, inversely proportional to the Z. And we know that load sharing by first transformer is given as total load S load into Z2 by Z1 plus Z2. Okay, that second transformer load is going to shared as load into Z2 by Z1 plus Z2. Okay, so from this you can say that this per unit impedance we can't substitute directly here. We need to calculate it into ohmic values. Okay, we need to calculate into ohmic values. When you calculate in ohmic values, okay, so the load sharing will maybe depends on the kVA rating. Okay, kVA rating of each transformer. So the load sharing will be in proportion to the respective ratings. Whenever per unit impedance is same, then kVA rating, it depends on the kVA rating of each transformer. The next question is about 1100 kVA 11 kV by 1.1 kV conventional two winding transformer is connected as 12.1 kV by 11 kV step down auto transformer. Okay, this is the one of its kind of question Normally they will ask step up connection, but they are telling it is step down. The rating of the auto transfer. So whenever a question comes on the auto transformer, we need to remember that it is having the same winding for both primary and secondary. Okay, let's write down the circuit diagram of the auto transformer for a given data. Okay, what is the given data? The same portion of winding will act as both primary and secondary. What is the primary in both sides? Here it is primary of 211 kV. It is going to be 11 here. Okay, 11 kV is the common voltage for both primary and secondary. What is the extra voltage we are having? It is about 12.1 kV. 12.1 kV means 1.1 kV it would be here. Okay, this is the secondary of auto transformer. Is it clear? Next, the thing is whether it is summation or subtraction. So if you see 11 plus 1, 1.1, it will what? How much it will come? It is coming around 12.1 kV. Okay, so the secondary side is series additive. Series additive means dot connection will be like this. Okay, dot connection will be like this. This is the primary side, this is secondary side. So in order to calculate the kV of the auto transformer, just remember the simple formula what I am going to explain here. You can solve any question related to the auto transformer. So KVA rating of auto transformer is equal to KVA rating of two winding transformer into secondary voltage of auto transformer divided by common voltage. What is the KVA rating given? 1100. What is the secondary voltage? Okay, just first we will do calculation for 11 by 12.1 kV. That means primary is 11 kV, secondary is for 12.1 kV. This is the secondary. So the same transformer we can use for both step up and step down transformer. For easy calculation, first I am considering for step up transformer, and we can convert. Why? Because KVA is same for either it is a step up transformer or step down transformer. The KVA is going to be same. So for our convenient purpose, I am writing like this. Okay, secondary is 12.1. Common voltage here. Common voltage is 11 kV. From here I take it. Okay. All are in kilovolts or the kilo kVA. So no need of any multiplication here. So what will happen? 11 in, you can calculate here it as 100. It is going to be 121 into 100. So percentage, sorry, not percentage, it is about KVA rating of auto transformer equal to 12,100. Okay, so what I calculated for step up. For the KVA is same for whether the transformer is a step up transformer or step down transformer, but for clear understanding I have taken it as a step up transformer and calculated the KVA. Is it clear? Okay, let's move on to the next question. The next question is about the energy density of magnetic field in a magnetic circuit. Okay, what is that asking? Energy density and relation with the magnetic field. Magnetic field and magnetic flux density. Okay, so we know that Actually, this type of questions will come very rarely. So, from the magnetic circuits, we know that energy density U is directly proportional to B square by mu. Okay, B square by mu, where B is the U is the energy density. U is the energy density. B is the flux density. Mu is permeability of the circuit. Permeability of magnetic circuit. Okay. So let's see the given options. They are telling inversely proportional. No, it is a directly proportional. This will be ruled out. The second option is directly proportional to the absolute permeability. No, it is inversely proportional. This is also wrong. Directly proportional to the magnetic flux density. No, it is the square. So our option will be D. So energy density is directly proportional to the square of the flux density. Okay, the options will be D. Okay, let's move on to the next question. The next question is about the main purpose of using core in a transformer is to. Okay, what they are asking, purpose of using core in a transformer. Purpose of using core in a transformer. Why you need to use the core? Why you need to use the core means, if you see a transformer construction, what is going to happen? We are converting electrical energy to magnetic energy. First step, what you are doing? We are converting electrical energy to magnetic energy, and from magnetic energy it is going to again converted to electrical energy. Okay, this is the energy conversion happening in the transformer. So if there is no core in between, what will happen? It will be the medium of transfer of magnetic energy will be air. If there is no core, what will happen? The medium of transfer of magnetic energy from primary to secondary is going to be air. Okay, we know that when air is having more reluctance, air is going to having the more reluctance. Okay, very small portion of magnetic energy is going to transfer from primary to secondary. If you are using a air as a medium of transmission, then what will happen? Very small amount of magnetic energy will going to convert to electrical energy. So total what is going to happen? The efficiency of the transformer is going to be very less. Okay, efficiency of the transformer is going to be very less. So in the energy transmission process, especially in a transformer, we need a solid medium so that it can transfer efficiently the magnetic energy generated at primary side to secondary side. Okay, primary side to secondary side. This is about the importance of core. Let's see the given options. Decrease the iron losses. No, if it is core is not there means our efficiency is reducing. No, it is not important, not correct option. Eliminate magnetic hysteresis. This also may not be suitable option. Reduce reluctance of the common magnetic circuit. So our option will be C. The most suitable option is C. Why? We already seen here. We need to transfer the magnetic energy from primary to secondary efficient manner means we need a core with having high permeability, which is having high permeability. For air, permeability is very less, so reluctance will be high. Only small portion of magnetic energy generated from primary to secondary is going to be transmitted. That transmitted energy converted to electrical energy. But the efficiency, if you see the total electrical energy conversion, it will be very less. So the most suitable option in the given question is C, to reduce the reluctance of the common magnetic circuit. The next question is about when a VV three-phase transformer system is converted into delta system, increase in capacity of the system is. Okay, increase in capacity of the system is. In previous sessions already we solved so many times this type of questions. We'll write down the circuit diagram first. What they are telling, VV type to delta conversion. This is the VV type transformer. Okay, this is line voltage VL, line current IL. This will be the line current I1. Let's see about delta. Delta transformer is like this. This is the line voltage, this is the line current, this is phase current. The relation between line to phase current is root 3 I1. Okay, let's calculate the kVA. We already discussed in the previous session. The kVA is, you can calculate for three-phase system is kVA for VV type is equal to root 3 VL IL. What is VL? VL is VL, IL is I1. Okay, so you can write IL here is I1. And similarly delta kVA is going to calculate as root 3 into VL is VL, IL is root 3 I1. It will be 3 VL I1. So therefore let's take it is equation 1, let's take it is equation 2. Let's do 1 by 2. What will happen? Root 3 VL into I1 divided by 3 VL I1. Okay, let's calculate this. It will be 1 by root 3. Okay, so it is going to, therefore they are asking about delta, so we'll write in terms of delta kVA. Therefore delta kVA equal to root 3 times of VV type kVA. It will be around root 3 is nothing but 1.732 into VV kVA. So if you write in the percentage, how much it will come? The percentage, if you write, it will be 73.2% more than the VV type kVA. Okay, delta kVA is 73.2% more than the VV type kVA. So our option will be D. Is it clear? In previous sessions, the most of the questions are ulta. That means they given delta system and they asked about the VV type capacity. But in this question, they given they are telling VV type transformer is there. Then if we convert this VV to delta, how much percentage kVA transmission will get increase? So how much percentage it will get increase? It is around 73.2%. Is it clear? Okay, let's move on to the next question. The next question is about 3 kilowatt load is supplied by an auto transformer with 0.7 transformation ratio. Conductively transferred power from primary to secondary. If you read out the question carefully, what they are telling, they are asking about conductively transferred power in a auto transformer. What is the concept about auto transformer? Power transfer by conduction process. We already discussed in conduction process. In the auto transformer, the power is going to be transferred both conduction process as well as induction process. So they are asking about conduction transformers. So let's write down the given data. The given data is load is 3 kilowatt. Okay, load is 3 kilowatt and transformation ratio is given as K is 0.7. Okay, we know that. What is the formula? We know power transferred through conduction is equal to the K into total load, total power or total load. Okay, so what is K? 0.7. The total is 3 kilowatt. Okay, how much it will come? It will come around 2.1 kilowatt. Our option is A. Is it clear? So when I sincere advise when you are getting auto transformer question is, let's clear about the concept. Okay, let's clear about the concept. Near about only 4 to 5 synopses are there for auto transformer. That means how much is the power transferred to conduction process, how much percentage of copper we are saving by converting two winding transformer to auto transformer, and how much kVA rating is going to be increased if you are using auto transformer. Okay, third one is about efficiency and reduction of losses. Okay, like this 5 to 6 synopses are there. If you remember these synopses, you can solve any question related to the auto transformer. Most of the times the question is repeatedly coming like this only. Let's move on to the next question. The next question is about a transformer of rating 2200 divided by 220 volt 22 kVA has total loss of 1 kilowatt. Okay, total loss of 1 kilowatt at full load and unity power factor. The power factor is given as unity. If it is reconnected as an auto transformer with a supply voltage of 220 volts and secondary voltage of 1980, efficiency at full load. Okay, what they are asking, you need to calculate efficiency at a unity power factor. Let's note down the concept given. What is the concept behind this question is calculation of efficiency of auto transformer. What is the formula we know for calculation of efficiency? Percentage efficiency is equal to kVA into power factor, output kVA into power factor plus total losses. Here if you see total losses of two winding transformer, they already given us 1 kilowatt. Okay, total losses given as 1 kilowatt. These losses will be same whether it is a two winding transformer or a auto transformer. This losses is going to be same. Okay, this losses is going to be same for auto transformer also. What we need to calculate? We need to calculate the kVA. Okay, you need to calculate the kVA. I already explained in the previous question also. kVA of auto transformer can be calculated as kVA of two winding transformer into secondary voltage of auto transformer divided by primary voltage of common voltage of both auto transformer common voltage of both primary and secondary. Both primary and secondary. If you observe the question, in both the common voltage will be 2200. Why I am telling is, in both cases it is reflecting 2200. Okay, so let's substitute the given data. kV of two winding transformer is 22. Secondary voltage of auto transformer is 1980. Common voltage will be 2200. By solving this, how much you will get? Okay, it will be 22 into kVA means 10 cube. Common voltage is 2200. How much it will come? 1. It will come 1980. Okay, it will come like this. So let's substitute the kVA into efficiency formula. Percentage efficiency is equal to 1980. Power factor is 1. Sorry, 198,100. Total losses is given as 1 kilowatt, that is 1000. By solving this, we'll get percentage efficiency is about, how much it will come? Let's calculate. It will come around 0.995. 0.995. So our option will be B. Is it clear? Okay, let's move on to the next question. The next question is about which of the following statements are correct with respect to a single phase transformer. Which of the following statements are correct? Correct statements we need to find out regarding single phase transformer. The first option they are telling is the primary ampere turns are significantly more than the secondary ampere turns. Okay, primary ampere turns. They are telling, you need to note down carefully. It is a ampere turns, significantly more than the secondary ampere turns. Okay, we know that the transformation ratio I1 by I2 is equal to N1 by N2 in transformer. From this, what you can write? N1 I2 equal to, it will be like this. I1 by I2 equal to N2 by N1. From this, N2 I2 equal to N1 I1. So this is the the ampere turns. Ampere turns means current into number of turns. Will be same for both primary and secondary. But in the question they are telling it is more. So it will be wrong. It is not correct option. Let's move on to the next option. The flux in the iron core remains the same for no load and full load conditions. If you study, you might have studied in our theory concept that the flux in the core is always constant. Okay, the flux in the core is always constant irrespective of the load condition. So this may be correct option. Let's look after the third option also. When two single phase transformer operated in parallel, the transformer having greater leakage impedance shares more load. Okay, what they are telling, if leakage impedance is more, it will share more load. No, we know that Load sharing is inversely proportional to the impedance. If it is having low impedance, then load sharing will be high. So this option also wrong. So finally, what is the correct option among these three is only 2, that is B option. Is it clear? Let's move on to the next question. The question is about consider the following statements. Okay, they given 3 statements, and among those we need to select which are the correct options. Transformer is a doubly excited magnetic system. Doubly excited magnetic system. First of all, we need to understand what is mean by doubly excited. Doubly excited means two energies we are giving input to a single machine and we are going to take a single output. Okay, that means we are providing two inputs, two energy inputs to a one machine and we are taking out single output. Okay, so in a transformer, if you observe, there is no only we are giving electrical energy as input and we are converting it into again electrical energy only. Okay, only single input is there. So transformer is not a doubly excited magnetic system. It is wrong. Second option is synchronous motor is a doubly excited system. If you might have studied in our theory concept that for synchronous machine, what you have to give, we need to give field flux. Field flux we need to going to generate by using DC excitation. DC excitation. This is one input, and secondary input is prime mover. By using prime mover, we are going to providing the mechanical energy. Okay, so synchronous motor is a doubly excited. Synchronous motor is a doubly excited. Okay, we are going to provide DC excitation. They are asking about particular about motor. Motor means what input we are going to give? Electrical energy. 3-phase electrical energy. Also one more input we are going to give. So synchronous motor is a doubly excited magnetic system. Next, third option is relay is a singly excited magnetic system. Relay is a singly excited magnetic system. We might have studied in our theory concept. So the third option also correct. So our suitable option is 2 and 3. The correct statements in a given question are synchronous motor is a doubly excited system, doubly excited magnetic circuit, and relay circuit is a singly excited magnetic system. Okay, 2 and 3 are correct. The first one is wrong. Okay, let's move on to the next question. The next question is about a single phase 200 by 125 volt auto transformer delivers 40 kVA to a load at 0.8 power factor lagging. Neglect the leakage reactance and magnetizing current. For this loading condition, the transformed kVA of, so they are asking about transformed kVA of 2-winding transformer. Okay, the transformed kVA of 2-winding transformer. We know that auto transformer kVA is auto transformer kVA equal to kVA of 2-winding transformer into secondary voltage of auto transformer divided by common voltage. From this you can calculate a kVA of 2-winding transformer can be written as kVA auto into common voltage divided by secondary voltage. kVA auto, how much they given? 40 kVA. What is the common voltage? Common voltage will be 200. Okay, common voltage will be 200 And what is the secondary voltage? We have to take what you have to take? You have to take 325. By simplifying this, we are going to get it as 15 kVA. Okay, we are going to get it as 15 kVA. So our option is A. Let's move on to the next question. The next question is about a 220 by 110 volt 50 Hz transformer is connected to a supply on the high voltage side. If it is operated primary voltage of 220 volts and 5% less frequency, the secondary no load voltage is found to be E21. Okay. Operated primary voltage 110 volts, 50% less frequency, the second voltage is going to be E22. They are asking the ratio of E21 by E22. So in previous session also we explained that the flux density B is directly proportional to E by F. So in order to get proper operation from the transformer, E by F need to be maintained constant. Okay, maintained constant. If you are not able to maintain V by F ratio constant, that means in both cases frequency is reducing. So it means that the transformer will demand high magnetic flux. That means it will demand high magnetizing current from the source. So in the question they are telling the frequency is reduced and EMF they want to operate at a low frequency, means the system need to be ready for high magnetizing current. Okay, so if you are able to supply high magnetizing current, then there is no issue in the operation of the transformer. Okay, so except this, it is normal transformer only. Yeah? Except this high magnetizing current, the operation is going to be normal as normal transformer only. So from the given data, let's calculate the transformation ratio. The turns ratio. What is the turns ratio? E1 by E2 equal to 220 by 110. It's going to be 2. In first case, E21 can be calculated as they given primary voltage at 220. So secondary voltage will be how much? 220 divided by 2, it is going to be 110 volts. In second case, E22 is equal to 110 divided by 2, it is going to be 55 volts. Therefore, E21 divided by E22 equal to 110 divided by 55. It will come around 2. Option is D. Is it clear? Okay. So to confuse the students, they are going to frame the questions like this. Okay. They are going to frame the questions like this. In practical case, that may not be suitable for the operation of the transformer. But they are asking a question like that, means we need to solve the question by using some assumptions. Okay. So even the frequency is reduced means flux density will be high. So in order to meet that much flux density, we need to the transformer need to draw the high current from the source. This may not be normal operation, but in the examiner ask the question, so we have to solve like this. This may not be affect the transformation ratio. So from the given data we calculate the transformation ratio. From there we calculated E21 and E22. Thereby we calculated ratio of E21 by E22. So our option is D. Is it clear? Okay. By this question we are going to stop today's session. Okay. Tomorrow we will start again morning 6 o'clock. We will solve some more questions related to the electrical transformers. If you have any doubt, okay, please comment over the chat box. We are ready to help you. And please share the video to your friends It will be helpful to them also, and it will be little encouragement to our ours to do more sessions on this previous year questions. Okay. As a GoVidya, we are providing offline coaching and online coaching and test series. So if you want any help regarding your preparation, you contact our number as shown in the screen. Okay. Thank you.